Chapter 9 deals mainly, at the very beginning part, deals mainly with the shapes of molecules. And so what we're going to be looking at for these first couple of sections is we're going to be talking about what a molecule actually looks like. So if we were small enough and that we could actually see an actual molecule in the air or in a table or anywhere, we could actually look at that and go, oh, that looks like a, and then whatever shape it happens to be. So 9.1 and 9.2 are all about different shapes. What we're going to be using to do that is we're going to be using the electron domains in the valence shell, and then we're going to be using those electron domains to predict the molecular shape based on its Lewis structure. So hopefully now we can use Lewis structures to show the bonds between atoms in a molecule. So we can draw CO2 and we can make CO2 and we can show the bonds between the carbon and the oxygen. We can show the electrons on here. But what we don't know is what a CO2 actually looks like. And what I mean by that is CO2 may look like the picture that I just drew, where you've got a straight line. CO2 theoretically could be a bent molecule that looks like this. There's different ways that we could actually draw this molecule to show what it really looks like, and that's what we're missing is the shape. And so that's what this section is going to be referring to, is to the shapes of the molecules. The overall shape of a molecule is determined by the angles. And so right here, when we talk about the angles, that is the bond angle between the two oxygen atoms. And that one, the way I drew it, would be somewhere right around 90 degrees. This one, again, just the way I drew it, is about a 180 degree bond angle. So it has to do between the bonds between two different atoms. So what we're going to do is we're going to accurately define the shape of the molecule using bond angles and the length of the bond. And just for example, we haven't got to this yet, but carbon tetrachloride has a tetrahedral shape, which we'll talk about here in just a second. And the bond lengths on there are about 1.78 amperes. Okay, the model that we use for describing the shapes of molecules is called the VSEPR model. I realize the S is before the E, but that's just how the man pronounces it, is with VSEPR. And it stands for the valence shell, again, so the outer shell of electron pairs that repel each other. So that's the model that we use, and basically the atoms and the electrons want to form in such a way so that the electrons are out of each other's way the most part. When you're using the VSEPR model, double or triple bonds still count as if they were single bonds, and we'll see that here in just a minute or so. So we're going to start with simple molecules, and we're going to go through those. Some of those, and the easiest way to do it is, let me just clear this screen. Don't really worry necessarily about what's in your notes. I'm going to try to explain it in a little bit different way to hopefully help you understand a little bit better. Basically, there's one, two, three. There's basically 5 shapes. The first shape is based on, and they're all based on one central atom. So let's say you've got you've got beryllium in the middle, you've got a fluorine out here, and you've got a fluorine out here. The way that you would look at this is you would say, we're only looking at the central atom here first of all, and we're looking at the number of bonds, and we're looking at the number of non-bonding electron pairs on the central atom. Okay, so it's the number of bonds, and again, maybe I should put on the central atom, and the number of non-bonding electron pairs on the central atom. So on BeF2, let me move it down here real quick. On BeF2, we saw that there was the 2 bonds, and again, remember, if it's a single bond, a double bond, or a triple bond, it only counts as 1 bond. So we count 1, 2 bonds. So the number of bonds on the central atom is 2. the number of non-bonded electron pairs on the central atom. So that would be something like this. If I put 2 dots here, that would be 1 non-bonding pair. That's a pair of electrons that are not bonding. So it's the number of non-bonding pairs. In this case, it's actually 0. Anytime you have a molecule that forms 2 bonds and has no non-bonding pairs on the central atom, the shape of that is called linear. Okay, because it forms a straight line. Remember that the electrons want to be as far apart from each other as possible. So the way that can happen is that bond angle right there is 180 degrees. Okay, so that's the first one. Remember, there's 5 of these. The next one, which is, again, it looks very similar once we get all said and done here, is something such as AlF3. Which again, we put all our dots on here. And actually, let me change it. Instead of aluminum, let's do boron. Okay, that's boron trifluoride. It's got how many bonds on the central atom? I count 1, 2, 3. Number of non-bonding pairs on the central atom. Let me get rid of these arrows. How many dots are on the central atom? I see none. And what that forms is it forms a triangle, as you can see, forming a triangle. So it's called trigonal. And it also is flat, a flat triangle. If something is flat, many times we call it planar. So that is called trigonal planar. And that is, and just like I said, it's perfectly flat. There's nothing going up or down here at all. Okay, so we've got 2 bonds, we've got 3 bonds. Let's go to 4 bonds now. With 4 bonds, you've got something like methane, where you've got a carbon and it's got 4 hydrogens attached to it. Now the problem with this here is if we look at the shape, I can actually show you the molecule in class, is this is a 3-dimensional shape. And so what we do is with this hydrogen that's down here, we try to make it look like it's sticking out from the screen here a little bit, and so we make that weird looking triangle, and I know that doesn't really help, but then we make a little dash line here, and that hydrogen theoretically is sticking back into the screen. So this hydrogen here is poking out, that one is going in, and so what you've got is you've got 4 bonds on that central atom, and you've got no dots on the carbon. So all total it is 4. So we end up with a tetrahedral. Tetral meaning 4, hedral is just a name for a different, or for a figure. So it is a 4-sided figure called a tetrahedral. Okay, and that's it for 2, 3, and 4. Now we've got 2 more, and that's going to kind of set us up for all the rest of the shapes, because after these 5, there's about 1, 2, 3, 4, 5, 6. So there's about 8 more shapes after that, but all 8 of them are based on the shapes that we're learning right here, right now. So 2, 3, and 4. Let's go to 5 now. So again, same thing as before, bonds and non-bonding on the central atom. And you'll notice that so far, everything that we've done under the number of non-bonding pairs on the central atom have all been 0. And that's okay, because we're going to get to other ones here in just a little bit that don't have 0. So if we go to something such as PF5, we've got a phosphorus in the middle. We're going to have 1 fluorine sticking straight up, 1 fluorine sticking straight down, 1 sticking straight to the side, and then kind of like on the tetrahedral, we're going to have 1 sticking out here. Do we have to put all the dots on here? Yes, you do. And then 1 going into the board, kind of like that. So what you can see, hopefully you can see 1 going up, 1 going down, and then these 3 here in the middle, those ones right there are forming a triangle. So we've got 5 bonding pairs. We've got no non-bonding pairs. And the shape of that, again, if you can visualize it, is you've got the triangle here in the middle. So it's called trigonal. And then with that triangle going down is you've kind of got a pyramid. So you've got a pyramid going down, and you've also got a pyramid going up. And so two pyramids, the way they would say that, bi means two, and pyramid, so that's called trigonal bipyramidal. And then our last one, 6 bonds, no non-bonding pairs. SF6 is what it would be. 1 going up, 1 going down. And then you've got 1 sticking straight sideways, another one sticking straight sideways, and then you've got 1 coming directly out of the board straight at you, and 1 going back into the board straight behind you. And that one is called octahedral. Octa meaning an 8-sided. If you put sides on this, it would have 8 sides. And a hedral is just the shape. Okay, now let's talk a little bit about bond angles here. On the linear one, we had written that it would be 180 degrees. Here, because you've got 3 bonds, they're all the same size, that would be 120 degrees all the way around for each bond. This one, because it's 3-dimensional, is a little bit weird. That bond angle actually is, and this is on the test a few years ago, 109.5 degrees. And they accepted any answer from 109 to 111, I think is what they took. But 109.5 is the actual correct bond angle for a tetrahedral. So we got 180, 120, and 109.5. And then here for this one, these are called the equatorial ones, which are the ones pointing up and down. Between the equatorial ones and the ones in the triangle, obviously that's a 90-degree angle, but then within the triangle itself, it's back to 120 degrees. And then this one here, obviously they're all 90 degrees. So those are all pretty clear. Hopefully they're pretty straightforward. So if I were to ask you shapes right now, and I just said something like CCl4, hopefully right away you'd go, oh, well, 4 bonds, that's got to be a tetrahedral. The problem is these right here, these non-bonding electron pairs. And that's why it's absolutely crucial that when you do these problems, that you don't just look at how many bonds it makes. Because for these 5, it's real simple, because there are no non-bonding electron pairs. But if I say something such as water, well, with water, you've got H2O. When you draw the Lewis structure for water, you've got this, and then you've got those. On all the examples we've done so far, we've had no dots on the central atom. So now what we're going to be looking at is we've got our 5 basic shapes. So let me write the first one is like CO2 or something like that. Carbon dioxide. How many bonds does it have? 2. 1, 2. How many non-bonding pairs does it have? None. So that is a linear shape. And really, there's nothing we can do here. If we take one of these bonds off and we just made carbon monoxide and we said, okay, what's the shape of that? Well, there is no shape. There's just 2 bonds there and nothing else really to go with that. Okay, but if we take our, for example, if we take our BF3, let's take BF3, which was a trigonal planar. It's got bond angles of 120 degrees. And let's say, and again, we've got 3 bonds and we've got 0 non-bonding pairs. What if we take that and instead of one of these here being an electron pair forming a bond, what if we made it a non-bonding pair, such as the ozone molecule? So let's first of all draw the ozone molecule. It's got 18 valence electrons. You've got O, O, O. We're going to complete the octet out here. Now we're going to count up our electrons. I've used 16. I have 18. So with the 2 I have left, I'm going to put the 2 dots right there. Now I've used all 18. This central atom does not have 8, so I'm going to take 2 of these and make a double bond. So now if we're counting bonds, how many bonds does this central atom make? 1. And remember, a double bond counts as 1. So there's 2 bonds. And how many non-bonding pairs do we have? We've also, in this case, got 1. Not also, I should say. We just have 1 non-bonding pair. So now the key to understanding what shape this is it's basically the same shape as what we've done up here. But instead of one of these being a bond, now it's just a non-bonding pair. So what this shape actually looks like is it looks like a trigonal planar with one of the bonds taken off. So you have something that looks just like that. And it's basically a molecule that you've bent. So the shape that we would call that is we actually call it a bent molecule. Okay, the key to understand this again is it's basically one of these with that part taken off and now these. Now, what you might want to ask yourself is they would never ask you specifically what's the bond angle here, but what they could ask you is they could ask you in reference to a trigonal planar that is 120, would this bond angle here be more than, less than, or equal to 120? And if you think about it, think about electrons. These electrons have a lot more room to move around now because they're not in a bond. And electrons repel each other. So these electrons that are now a little bit freer to move around are repelling those electrons, and they're repelling these electrons, which pushes this bond closer together. So that bond is actually going to get a little bit smaller. So it's going to be less than 120 degrees. And I think it's actually like 117, but again, they would never be that specific. But you should be able to not only say it's less than 120, but you should be able to say why, which is simply because of the increased repulsion between the electrons. Okay, so within the trigonal planar shape, let's just say, X and Y, you can actually have 2 different shapes. You can have the trigonal planar shape, and you can also have the bent shape. Now again, just like on the linear one, if I take that one off, now I'm just down to no shape at all. Okay, so far we've talked about the 5 basic shapes. We've talked about linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. Now we've taken one of those shapes, the trigonal planar, and we've reduced it to something simpler. But again, this shape is based on that shape right there. Okay, let's look at some other ones then. Okay, if we have a tetrahedral, the tetrahedral that we saw was the methane molecule, CH4, looks like that. The bond angles again were 109.5. There were 4 bonds, 0 non-bonds, and the shape was tetrahedral. Now let's, instead of again having 4 bonds this time, let's have again a total of 4, just like in the previous one. The previous one we had a total of 3. In the first example it was 3 bonds and no non-bonding pairs. In the second example it was 2 bonds and 1 non-bonding pair. So basically we want to do the same thing here. We want to have 3 bonds and 1 non-bonding pair. Okay, an example of that would be phosphine, which is PH3. And what phosphine looks like is something like this, which is basically, again, notice the shape. It's a tetrahedral with that top part right here taken off. Okay, and what that forms, as you can see, it's forming the triangle here along the bottom. So you've got a trigonal, but it's not flat. It also is forming a pyramid. And so what that is called is it's called trigonal pyramidal. Now, do not confuse that with the trigonal bipyramidal. Remember, trigonal bipyramidal is when you have the 5 bonds and the no non-bonding pairs. Trigonal pyramidal is only when you have 3 bonds and 1 non-bonding pair. Now we can take another pair off of here. So instead of having 1 non-bonding pair, we're going to take another bond and turn it into a non-bonding pair. So we're going to have 2 bonds and 2 non-bonding pairs. The most classic case of that is water. Okay, water looks just like that. And that, for example, we've taken this hydrogen off right here, and we basically just turned it a little bit to make that. Okay, so water, as you can see, has 2 bonding pairs and 2 non-bonding pairs. Again, the key is how many does it have all total? 4, 4, 4. All of the ones that add up to 4 have this tetrahedral shape associated with them, and you simply are removing bonds each time you make a different shape. So there's the water molecule again, but again, you've got to put those dots on there. Okay, so we've got 2 bonds, 2 non-bonding pairs. As you can tell, it actually looks very similar to the previous page when we had 2 bonds and 1 non-bonding pair. It is also bent. Okay, so there's actually 2 of them are called bent. Now again, how might they ask us on the exam is they might have you compare the bond angle in ozone to the bond angle in water. Which one's got a greater bond angle, here or here? Well, you would hopefully say something along the lines of, well, water has 2 lone electron pairs, ozone only has 1. The more the electron pairs, the greater the repulsion, the more they're going to be pushed in. So water would have a much, much smaller bond angle than ozone would, simply because water's got the 2 electron pairs, ozone's only got the 1. And again, now we're to the point now where if you take another bond off and we had 1 and 3, we don't really have a shape at all, so we're done with the 4 bonds or 4 electron domains. So let's go to 5, which again, there's a couple of those as well. So the one we saw for 5 was trigonal bipyramidal, sticking out, one going in. So we've got bonds, non-bonds, and shape. So here we have 5 bonds, 0 non-bonding pairs, and the shape, as we said, was trigonal bipyramidal. Now, instead of all of them being bonds, we're just going to make a molecule that has 4 bonds and 1 non-bonding pair, such as SF4. Now, the problem here is that you've got to be very careful about which bond you take off, because you've got the one pointing up, the one pointing down, then you've got the triangle in the middle. The key is you always remove electrons from the triangle first. So we're going to take that fluorine off right there and basically turn the whole molecule this way. And what it's going to look like is you're going to have, instead of them pointing up and down, these 2 are now pointing sideways. And the reason that we do this is because now one of these is pointing out, one of them is pointing in. And again, the reason that we do that is because we now have this 1 lone electron pair here. The shape is relatively the same, except for that fluorine's not there anymore. We've got our 1, 2, 3, 4 bonds, our 1 non-bonding pair. And again, the reason that we draw it this way is because it looks just like a teeter-totter, or the chemical name is actually called seesaw. So we take that one bond off, and now we've got a seesaw shape where you've got these two would be the up and the down of the seesaw, and then these two would be the supports of the seesaw. Okay, so let's take another one off. So we're going to take, let's say that fluorine right there is going to go. So we're going to have 3 bonds and 2 non-bonding pairs. Something such as BRF3 would have the BR, F, F, F. There's our 24 electrons, and you're going to have 4 left over. So those 4 have to go on the central atom. And again, I took off part of the triangle again. So we've just got one part of our triangle left. Here's the up and the down fluorine still. 3 bonds, 2 non-bonding pairs, looks like the letter T, and it is called T-shaped. So again, you draw a Lewis structure, you see 3 bonds and 2 non-bonding pairs. I think of it as a trigonal bipyramidal, but then I take 2 of those bonds off and it becomes T-shaped. And then our final one for this one is you can take this last fluorine off as well. So something like XeF2, you've got the Xe. So you've got your 16 electrons there. You've got 6 left over. So you've got 1, 2, 3, 4, 5, 6. So you've got 2 bonds, 3 non-bonding. So basically the whole triangle is gone. The only thing that's left is that fluorine and that fluorine. So you're all the way back to a linear shape. Okay, and this is something that you're going to have to study. This is not something that the first time you see this, you're going to go, oh, okay, I get it, no problem. Okay, you're going to have to work at this, and you're going to have to know all of these shapes. Okay, because we've got 2 more. Because we've done linear, we've done trigonal planar, we've done tetrahedral, and we just did all of the trigonal bipyramidal ones. If you feel like your brain needs a break, just pause it and come back. But there is a couple more that we need to know. Okay, so let's just go back. Let's see. Let me just find a spot here. So if we come back here, the very last one was the octahedral, where we had the S and the F, up, down, and then straight out at us, and then straight back. That was 6 bonds, no non-bonding, and the shape of that was called tetrahedral. And now that we have that, now we're going to remove one of those bonds. And again, these 4 here kind of form a square, and then you've got your top one and your bottom one. On these ones, the key is you take the top one, or it doesn't matter, the top or the bottom one off. So if you have something such as BRF5, you would have BR, and then you would have your 4 fluorines in the middle still. So the one sticking out, the one sticking in, and then you'd have your 1 fluorine still sticking up. So basically, this one down here, I took the bottom one off, and you've got your 2 dots down here. So you've got 5 bonds, and you've got 1 non-bonding pair right here. So 5 bonds, 1 non-bonding pair. Sorry, I'm getting a little lazy on my dots here. On the AP exam, you gotta put the dots on there. And then the shape of that is basically a square. These 4 are forming a square, and then they're also going up, and they're forming a pyramid. So that is called square pyramidal. And then our last one, when you have 4 bonds, and you've got 2 non-bonding pairs, 1, 2, you've got 4 and 2. You've still got your square, but now I've taken the top off. So it's a square and it's flat, so it is called square planar. So again, let's just review quickly what all these shapes are. You've got the linear shape, which is the most basic of all of the shapes. So you've got linear, which again is 2 bonds, no non-bonds. Then you've got trigonal planar, which is 3 and none. Within trigonal planar, you've also got the bent molecule, which is 2 and 1. So again, these are bonds and non-bonding pairs on the central atom. After trigonal planar, we've got tetrahedral. And within tetrahedral, we got 4 and 0. And then within tetrahedral, we had the trigonal pyramidal. That is 3 and 1. And then we also have the other bent, that is the 2 and the 2. And then after tetrahedral, we have, so this is 2, this is 3, this is 4. Once we get to 5, it's the trigonal bipyramidal, and that's with 5 bonds and no non-bonding pairs. And then within that, we have the seesaw shape, which is 4 and 1. We have the T shape, which is 3 and 2. And then we have the linear shape, which is 2 bonds and 3 non-bonding pairs. And then our final one is the octahedral, and that's with 6 bonds and no non-bonding pairs. And then the 2 that are within that one are the square pyramidal, and that's when you have 5 bonds and 1 non-bonding pair. And then you've got the square planar, which is 4 and 2. So let's say on the exam they give you something such as SCl4, and they say use principles of atomic structure to determine the molecular shape of this molecule. First thing you've got to do is you've got to draw the Lewis structure. Don't worry about shapes at all. Just go 6 plus 28 equals 34. S, Cl, 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 Cl. Put all your dots on there. I've used 32. I've got 34 though, so I've got to use those last 2 and put them on the central atom. Now that I've drawn my Lewis structure, now I can go, okay, what's the shape of that? Now, what you can't do is you can't look at that and go, well, I don't know, it looks like a square. It looks like I drew it flat. I think that's a square planar. What you've got to do is you've got to count. You've got to go 1, 2, 3, 4, 4 bonds, 1 non-bonding pair. So overall, if these were all bonds, you would have 4 plus 1. You would have 5 electron domains, which would be a trigonal bipyramidal. But if we take one of those domains off and make it a non-bonding domain, then you have a seesaw. So SCl4 is a seesaw shape. Somebody asked me once, what if you put teeter-totter on the AP exam? My answer, don't. Okay, let's see. So let's look at one more example. Let's look at OCl3, and we're going to put a minus charge on it. So OCl3 minus, just trying to get rid of all this other stuff here. So OCl3 minus is you've got an OCl. First of all, let's count the electrons. 6 plus 21. Remember that minus means we add one more, so that equals 28. So we've got 3 bonds. Put our 6 dots on the Cl. And there's 24 electrons, so I've got 4 left over. So 1, 2, 3, 4. So this time I've got 3 bonds and 2 non-bonding pairs. Therefore, OCl3 minus would be T-shaped. Okay, do you need to know all of these? Absolutely, Yes. Well, I don't know. Do you want to do well on the AP exam? If you do, then you better know all of these. But hopefully you're starting to see that all of the other shapes are based on the linear, the trigonal planar, the tetrahedral, the trigonal bipyramidal, and the octahedral. If you know those five and you can visually take bonds off of those, then you don't need to memorize all these other ones that come from them because they're all based on those original shapes. So we'll look at some of these tomorrow in class. We'll do some more examples. Try out the homework, please. Um, and again, use this page kind of as a reference. Look at the bonds, look at the non-bonding pairs, and then we'll talk about the rest of it tomorrow in class.